name is Mike Brett. I'm a professor of limnology in the Department of Civil and Environmental Engineering at the University of Washington. And I'm also on the external science panel for the Utah Lake Water Quality Study. And today I'd like to talk about quantifying nutrient inputs, nutrient retention, and sediment nutrient releases in Utah Lake using a mass balance approach. This approach is important because the nutrient fluxes in Utah Lake determine the frequency that this lake has toxic cyanobacteria blooms. Cyanobacteria blooms are strongly associated with nutrient concentrations, nitrogen and phosphorus in particular. These nutrients can come from natural sources. All lakes have natural sources of nitrogen and phosphorus, but high concentrations of nutrients in lakes are very often associated with anthropogenic inputs, such as wastewater discharges, agricultural runoff, stormwater, which I have misspelt. And the issue, as I've already noted, is the real issue that we're concerned about here is the incidence of toxic cyanobacteria blooms. So cyanotoxic production is a little bit more difficult to predict than just cyanobacteria biomass, but some cyanobacteria blooms produce toxins. This is Dolichospermum, which used to be known as Annabena, much easier to pronounce. And I've also got depicted here the toxin microcystin, the cyanotoxin microcystin, which is frequently detected at high enough concentrations to be of concern in Utah Lake. So the basic nutrient mass balance approach that I'm going to talk about today is a classic approach that we use in environmental engineering, also in chemical engineering. And it's very simple quantitative approach. It basically says that the change in concentrations in a lake or a reactor, I've got a depiction of a classic reactor in environmental engineering called a CSTR, continuously stirred tank reactor. So the change in the concentration in the system is equal to the mass flux of inputs minus the mass flux of outputs, which is the constituents that go out of the reactor, and the removal that occurs within the reactor. Okay, so we think of the lake as a simple algebraic reactor. And one of the classic assumptions that's made for these sorts of calculations is to assume steady state conditions, which just means that you assume that the system is more or less constant through time. So this happens if you were to example, average several years of data. In that case, this equation can be simplified to the inputs equal the outputs plus the removal. And so if we think in terms of, what do these terms actually represent? The inputs are the phosphorus inputs that come from external sources. And so I've already mentioned that these external sources could just be natural watershed weathering. This could be, atmospheric inputs of dust. It could be, it could also be anthropogenic sources. So common anthropogenic sources I've already mentioned before could be, discharge from agricultural sources, runoff from crops or animal feed operations, discharges from wastewater treatment plants, stormwater. Those are classic external inputs. And the outputs is just the water flowing out of the lake. So the water flowing out of the lake takes some of the phosphorus with it. And removal is the nutrients that get lost to the sediments of the lake. So they can be lost to the sediments. Sometimes they can come back out of the sediments through a phenomenon called internal loading that I'll talk about later on. But the major source, the major loss of nutrients in most lakes is to the sediments, especially for phosphorus. For nitrogen, you can also lose some of the nitrogen to the atmosphere. So this arrow could be pointing up as well. That can happen. And so I've already said that all lakes have natural inputs that come from, the production of nutrients by maybe vegetation in the watershed. So vegetation in the watershed can fix nitrogen, and that nitrogen can ultimately run off into the lake. You can also have phosphorus released from the watershed due to just weathering of the geologic matrix of the watershed. And usually these natural processes result in lakes with fairly low nutrient concentrations, and lakes that we would classify with a term called oligotrophic, which means that they would have clear water and a low biological activity, low concentrations of algae, and a low likelihood of having toxic cyanobacteria blooms. The top anthropogenic sources of nutrients to lakes around the world are, treated and untreated municipal sewage, agricultural fertilizers, waste from animal livestock feed operations, and when you're in more urban areas like the eastern shore of Utah Lake, stormwater drainage can sometimes be a very important source of nutrients. The outputs are just the outflow. So there's some portion of the phosphorus that remains suspended in the water, and that portion of the phosphorus gets advected from the lake. So the outputs counterintuitively actually represent the phosphorus that doesn't get removed from the water column. It's the phosphorus that actually stays in the water column. And this right here is showing the pumping station at the outflow of Utah Lake, which is the start of the Jordan River. And in removal is sediment or nutrients accumulation in the sediments of the lake, predominantly for phosphorus, also predominantly for nitrogen in most cases, although I did mention already that nitrogen can get lost to the atmosphere as well through a series of reactions that I don't really have time to describe right now, but that can be important in some lakes. And so if we think of this in terms of algebra, so we just thought of it in terms of in conceptually before, but in terms of algebra, the first equation I presented showed you that the change in concentrations equals the input flux minus the output flux minus removal. And this ends up looking like this equation here. So VDC out divided by dt equals QCN minus QC out minus sigma VC out. And that looks like, a bunch of gobbledygook with a Greek term thrown in there just to help confuse you. But the equation is fairly simple. V represents the volume of the lake or the reactor. Q represents the flow of water in and out of the lake. This equation is a little bit more complicated for Utah Lake because there's a lot of evaporative loss of water in Utah Lake. So the flow out of the lake is less than half the flow coming into it. So the mass balance is a little bit more complicated for that reason. And C is the concentration coming into the lake and the concentration going out of the lake. And in that sigma term, that Greek term represents the rate at which the nutrients are being lost to the sediments per unit time. And so I already mentioned that oftentimes what we do is we simplify this equation. So if we simplify this and say that we're interested in long-term averages, or the fancy term for that would be steady state conditions, then the input equals the output plus the removal. And if we express this, rearrange us a little bit, we can see that the output concentration equals the lake's concentration, because the lake is well mixed. So the water that leaves the lake has the average concentration of the water in the lake. And that concentration of the lake equals the input concentration divided by 1 plus a term called theta, which is water residence time. How much time does water spend in the lake, times sigma, the rate at which the phosphorus gets lost to the sediments. And if we put this equation in terms of phosphorus, we see the phosphorus in the lake is equal to the input phosphorus concentration over this 1 plus theta times sigma. And basically what this is saying is that the lake phosphorus concentration is strongly and linearly dependent upon the input concentration. So whatever input concentration you have to the lake, in any changes in an input concentration is going to be very influential in terms of determining the concentration in the lake. And also the loss rate to the sediments is very important. And that can depend a lot. That can vary a lot from one lake to another, depending upon characteristics of the lake, probably depending on a lot on what type of phosphorus comes into the lake. If the phosphorus is coming into the lake bound to sediments, then it's going to have a higher likelihood of just sinking to the sediments and staying there. If it's bound in mineral complexes that are difficult for algae to break apart and use, things like, reactions, mineral complexes with aluminum or mineral complexes with calcium or iron, the lake may have a particularly strong tendency to retain the phosphorus in its sediments. And another factor that's very important and varies a lot from lakes to lake, from one lake to another lake, is the amount of time available for the phosphorus to get trapped in the sediment. Some lakes have water residence times that are, a week or two, and other lakes have water residence times that are several decades. And so that has a tremendous impact on the difference between the lake's input phosphorus concentration and the lake concentration itself. And we can think of this also, very simply. If we assume, the flow is a constant for the system, that we have the same flow coming in as out, then basically the lake concentration is a function of the input concentration minus the concentration of phosphorus that got removed from the water by sediment, by nutrient accumulation in the lake sediments. And so this plot right here is an analysis I did some years ago of about 300 different lakes, looking at how the ratio of the concentration of phosphorus in the lake, or the output of the lake, divided by the input concentration, varies with the water residence time. And it shows that water residence time plays a very important role, although water residence time in this plot varies tremendously. So it just varies from a few days to, in the case of Lake Tahoe, 700 years. But the water residence time is very important because it determines how much time is available for the phosphorus to get lost to the sediments. If we plot Utah Lake in this plot, so that green point here in the middle of this plot, if we plot that, it shows that Utah Lake actually has very good phosphorus retention in its sediments. And right now, I'd say we don't know why that's the case, but one idea that's been talked about a lot within the Utah Lake Water Quality Study Science Panel is potential reactions with calcium carbonate that forms in the lake. So there's a lot of calcium carbonate forming in the lake. There's a lot of calcium carbonate that gets loaded to the lake, and phosphorus will react strongly with calcium carbonate. So maybe that's why Utah Lake is particularly good at removing phosphorus from its water. But we don't know that for sure. It's important to keep in mind, though, that the phosphorus concentrations in the water is the main determinant of phytoplankton biomass. And cyanobacteria blooms, which are the source of the cyanotoxins, are strongly associated with high phosphorus concentrations. They're also associated with high nitrogen concentrations. Although in that case, it's a little bit more complicated because cyanobacteria can do something called nitrogen fixation. So they can actually make their own nitrogen. So a little bit more complicated for the nitrogen side of the story. And we can use this mass balance approach to predict how much phosphorus concentrations in the lake would depend on the input concentrations for major point sources. So I have a plot here showing how the lake concentration, the input concentration to the lake would depend on the concentrations of phosphorus in the wastewater treatment plants that discharge to the lake. And you can see that there's a very strong dependency of the input concentration, which determines the lake concentration, on, in this case, the phosphorus concentration in the effluents of wastewater treatment plants. We can also use this mass balance approach to quantify how much phosphorus is actually released from the sediments back into the water column each year. So one of the concerns for Utah Lake, or any lake really, that is having problems with blooms is how much are the blooms being supported by phosphorus that just gets released from the sediments of the lake. And so I've already pointed out that Utah Lake is very good at trapping phosphorus in its sediments, but during the summer, some of that phosphorus that got trapped in the sediments earlier in the year or in preceding years gets released. And what I've done in this plot is I've averaged the last 5 years of data for Utah Lake collected by the Department of Environmental Quality. And I've been able to calculate that on average, the phosphorus release during the summer months in Utah Lake is about 24 micrograms per liter, or about a 42% increase in baseline in TP concentrations above baseline levels. And so there is some internal loading in Utah Lake. And very interestingly, I was a little surprised by this result right here. The internal loading that we see in Utah Lake actually tends to follow the algal blooms and not precede it. So classically, we would think of internal loading as a source of nutrients that supports the bloom. In this case, it's actually looking like the bloom is mobilizing the phosphorus from the sediment, so that the bloom is accessing phosphorus at the sediments, and it's the bloom that's driving internal loading instead of vice versa, which is, I think, very interesting. The amount of internal loading in Utah Lake it's significant, and it can definitely result in greater phytoplankton production during the summer. It can also result in a higher likelihood of a cyanobacteria bloom. But compared to some other lakes in the Western United States, it's pretty minor by comparison. So in this plot, I'm comparing the annual nutrient cycle for phosphorus for Upper Klamath Lake in South Central Oregon to that for Utah Lake. And I compare in both cases the average phosphorus concentration from month to month in these lakes to the average input concentration. And you can see in Upper Klamath Lake, there's a massive pulse of phosphorus that comes out of the sediments during the peak summer algal growth period. And in Utah Lake, there's a much smaller pulse of phosphorus compared to Klamath Lake. In Klamath Lake, it's almost 200 micrograms per liter. In Utah Lake, the pulse coming out of the sediments, like I said already, is only about 24 micrograms per liter. So it's almost a factor 10 less internal loading in Utah Lake than at Upper Klamath Lake. And we don't know the reason why it's so much smaller in Utah Lake, but it could be because the phosphorus that's bound to calcium in the sediments of Utah Lake is it's more difficult for that to be re-released back into the water. So my conclusions for this brief presentation are that Utah Lake has quite high phosphorus input from some sources. Some of the most important sources are especially the wastewater treatment plant discharges. The lake, conversely, the lake is naturally very effective at removing phosphorus from the water column. So if it weren't for this characteristic of Utah Lake, which is just a natural characteristic of this lake, the blooms would be much worse. So that's a little bit reassuring that it could be much worse than it is. However, the lake concentrations are still directly related to input phosphorus concentrations, and there are some sources that are having a big impact on the input concentrations to the lake, and also a big impact on the concentrations of the lake itself. Internal loading increases summer total phosphorus concentrations by about 42% on average. And in the grand scheme of things, this is an important source of phosphorus, but it's relatively small compared to some other large shallow lakes in the Western United States, especially Upper Klamath Lake, where I've done a lot of research in the last few years. So thank you very much for allowing me to have the opportunity to make this presentation. And if you have any questions, I should have left my email on here. My email is mtbrett@uw.edu. You can always find me just by looking for my website at the University of Washington. My name is Michael Brett. Just look me up at the University of Washington. You'll find my website, and you can ask me any questions you would like to, or call me up and talk to me about any of what I've presented in today's presentation. So thank you very much.